Hi folks, in this video we're going to cover some advances in positioning, which was our subject in Module 6. The research presented in this video is a collaboration between our group here at the University of Minnesota and Dr. Johannes Schoening's group at Hasselt University in Belgium. You might remember Dr. Schoening from his interview in the first module. Now this module, Module 8, is all about learning about spatial computing topics that are hot off the presses, and let me tell you, this work is truly hot off the presses. In fact, exactly 1 week before Module 8 went live, I will have presented our paper on this research at ACM SIG Spatial, which is one of the most important spatial computing conferences, and through its conference proceedings, ACM SIG Spatial is also one of the most important spatial computing publication venues. Now, if you're looking for recent developments in spatial computing, ACM SIG Spatial's proceedings are one good place to look. Now, recall from Module 6 that most modern smartphones use 3 types of signal-based positioning: satellite-based positioning, Wi-Fi positioning, and cellular positioning or cell tower positioning. Now, between these 3 types, your smartphone can figure out your position with decent accuracy in most cases. So, for instance, if you're indoors here, you can't see GPS or GLONASS satellites, but this isn't a problem. There are usually Wi-Fi networks in range to help you out, and there are probably cell phone networks available as a backup too. Same type of deal exists right in urban canyons. It's difficult to get satellite signals, but you definitely have access to Wi-Fi and cellular positioning. Similarly, if you're in a very rural area like this and there are no Wi-Fi networks in range, this is also not a problem, right? Chances are there aren't going to be a large number of buildings to block your global navigation satellite signals. Now, there is one type of place, however, that lots of people visit every single day where their smartphones can't establish a position, and what I'm referring to, as you might guess from the title of our research project here, are underground public transportation networks like the New York City subway, Berlin's U-Bahn, and so on and so forth. Now, because these subways are below ground, GPS is not currently an option, and similarly, in most cases, Wi-Fi networks are out of range, and anyone who has been on a subway knows that, except in special cases, there's generally no cell signal. This means that cell positioning is also out of the question. Now, if we could do positioning in underground public transportation networks, the applications would really be extensive. So the most obvious application is that positioning in these networks would put subway riders effectively back on the map. So for example, here is a screen grab from my iPhone that I took while traveling in the underground portion of the Chicago Red Line near downtown. While the phone apparently thinks that I'm over here, my actual location was around this location, and positioning in subway networks would solve this problem. Now, another application would be to help people who are traveling on very crowded subway cars know when to move towards the door. This is one that's particularly close to my heart. Positioning in subway networks would make developing an app that does this extremely straightforward. And similarly, one can easily imagine location-based advertising, right, taking advantage of underground public transportation positioning. So for instance, you can imagine getting pinged with coupons for restaurants at the next subway stop. The potential impact of these and other subway positioning-based technologies motivated us to develop a new technique that we call Subway PS, which takes the first steps towards finding a way to do smartphone positioning while people are traveling on subways. Now, at the beginning of this research project, we thought long and hard about how to determine a smartphone's position while it was traveling in an underground public transportation network. So for instance, one option we thought about was adding sensors to the environment. For instance, sensors that would fire each time the train passed a certain point, uploading that data to the internet, and then this data could be accessed by the positioning APIs in smartphones. However, this approach has 2 problems. First, you have to get the transportation agencies that run the subways to add these sensors and provide access to them, and this presents enormous bureaucratic and, of course, financial problems. Second, Wi-Fi and cell are, of course, more than just smartphone positioning technologies. They're also how smartphones connect to the internet, so the fact that they're not consistently available in subways means that this arrow here also won't work. Our solution ended up coming from an entirely different and, relative to our early thoughts, entirely unexpected direction. Specifically, we took advantage of the fact that when a train is not moving, it really doesn't shake back and forth at all, but when it is moving, it shakes back and forth in many directions. And for instance, on some subway systems in particular, it can do this shaking quite violently, right? Now, most modern smartphones contain 2 sensors that can actually help us detect this type of shaking. Specifically, they contain an accelerometer and a gyroscope. And you can see here from Apple's spec page for the iPhone 5 that the iPhone 5 contains both of these sensors. So for example, here is a smartphone's accelerometer readings for the X, Y, and Z axes from a 3-minute ride on the Central Line in London, England. These are effectively readings of the shakiness on each of these dimensions, and you can see clear gaps in the shaking in all 3 dimensions, right? As expected, these gaps map perfectly to when the train was stopped. What we did with Subway PS was implement some very straightforward methods that allowed us to detect these troughs in the signal, and combined with basic timetable information, this approach can give a smartphone position along a subway line, and one that is critically robust against unplanned stops and delays. Now, when developing positioning technology, and when developing most other technologies for that matter, evaluating the accuracy of your approach is absolutely critical, as is understanding its performance along a number of other dimensions. Now, as such, with Subway PS, we performed 3 separate evaluations that looked at different aspects of Subway PS, from stop detection accuracy to user experience. Now, with regard to stop detection accuracy, we found that we were about 85% accurate across 4 separate subway systems, particularly the subway system in London, Brussels, Cologne, and then the small subway we have here in Minneapolis. Now, this was particularly exciting to us as our current detection methods use very straightforward approaches, and there should be some relatively easy routes to improvement. We also looked at the accuracy of Subway PS across entire trips, and the reason we did this is that if Subway PS misses a stop, currently it actually can't recover, so the whole trip will be incorrect. Now, this can be addressed using relatively straightforward approaches. I'll talk about that in a sec, but we wanted to see how big of a problem this was. Now, we found on the Cologne, Germany subway system that Subway PS tracked about 80% of trips 100% accurately, when we define accurate as having predicted the correct arrival time within a 30-second window. Now, comparing this to the baseline of just interpolating location from a timetable, we found the baseline would only be about 42% accurate. So these timetables aren't very good for much. Now, in general, in much of my research, whenever possible, I like to use a mixed methods approach. And broadly speaking, this means that we don't just look at quantitative data like accuracy statistics and log information, but we also develop qualitative data. For instance, having real people use our systems and conducting interviews with these people. So to do so in this case, we developed a proof of concept application that takes advantage of Subway PS's position information called Metro Navigator. Metro Navigator has a number of features, the most basic of which is a visualization of your current position along the track up here. It also has a number of other features. For instance, it's going to notify you when there's an unscheduled stop, when you're crossing under a point of interest, and so on and so forth. Now, we also developed a smartwatch extension for Subway PS, so folks don't have to look at their phone to get basic subway positioning information. So we took a smartphone loaded with Metro Navigator to the Cologne subway system and asked people riding on the subway to use Metro Navigator while they went on their journey. Now, in total, 16 participants volunteered, and they gave us some valuable feedback on Subway PS. A great deal of this feedback was quite positive. So for instance, this participant here said, "As my GPS does not work here, this is like a GPS for underground trains. I want to have it integrated in Google Maps." You can imagine this was exciting for us. Another participant said, "It's just cool to see the train moving and stopping on the map. I feel safer when I can see that I've stopped close to the next station when we're stopped in the middle of a tunnel." This was an unexpected benefit for us. We didn't expect perceptions of safety to be a benefit of Subway PS, but we were, of course, quite happy that it did have that benefit. Of course, when Subway PS failed, the feedback wasn't so good. For instance, after Subway PS's stop detection missed a stop, this participant here said, "Oops, it seems like the system missed a stop. That's not so good. I would also be happy to help the system to detect the stops. If the system could help me get out at the right station, that would be totally fine with me." So the good news here is that while the participant wasn't happy with the failure, the participant also presented us with a new idea, crowdsourcing the collection of data to improve our stop detection. Now, our current stop detection techniques are very straightforward, and the next stage of the project will likely involve applying advanced machine learning techniques for stop detection. This participant has suggested perhaps one way to collect training data for our machine learning work. Now, another direction of future work for us is to integrate Wi-Fi positioning directly into Subway PS so that if a Wi-Fi network is available, for instance, at a subway station, we can use that to see if Subway PS missed a station so that one mistake won't cause a problem for the entire trip. Well, that's it for Subway PS. If you're interested in the details, a link to our paper is provided on the Readings webpage. Hopefully this video gave you a sense of the advances going on in positioning right now, as well as a sense of how this type of research gets done, especially at the early stages of a new area of work like subway positioning.